right here. We have a CH, COOR. I usually do R1. This is R3. This is R2. O. Okay, there is something like this. This is something like an airline. A plane is flying to sea. So we make it, we feel this, okay? An airline, an air going to sea. This is called wedge. Now, some people will say they're flying away from the terminal. Or like this. This is called slash. Okay, so there is two different types of the format. Now, what is SN means? What is R1, R2, R3? This is we using SN1, SN3, and the SN2 to represent. This SN represents 0 specific number. Stereo specific number. Okay, we will mention these. Those are very important positions. Okay, so let's talk about this. We move this one out. We have stereo specific number position 1, 2, and 3. What type of the fatty acid is going to attach to it? It could be saturated, it could be unsaturated. What are the positions? They do a lot of research because it's related to the melting points and also other characteristics of fatty acids. So there is some of the development during the progress of the research in the history. In 1960, people comes out this figure, which tells us the fatty acids inside of glycerols is actually very even distributed. So what that means? Let's say I have a fatty acids attached to it is A. If this A component is 35 more %, then it will become GAX2, X2, which means the other fatty acids. If this A component is 35 to 70 more %, then it becomes GA2X. If the components of A is more than 70 more %, then it's GA3. And you can see the curve is right there. They do the research, which is fatty acids in the molecular percentage, x-axis, and the y-axis is glycerols in more %. Then they come on those three curves. Okay? They think it's even distributed, which is distributed as widely as possible. However, later on, sometimes 90-70, close to 90-80, people find not really. They are random distributed, but it is restricted. So they say it is restricted random distribution. So what they find, which means these two positions, three positions, usually will be attached with different type of the fatty acids. They have some of the rules are easy to follow. So for example, in the vegetable oil, they find that the number 2 position is always unsaturated fatty acids. So 1 and 3 is either saturated or long chain mono unsaturated. However, when you see pig fat, which is lard, is different. pig fat is lard. What do you find? So position 1, SN1 and SN3 is actually unsaturated fatty acids. 18 column 1, which is oleic acids. And the position 2, which is actually dominant with more than 72%, which is actually palmitic acids, 16 column 0. Can you see that? But how about cocoa butter? Another vegetable oil. It's opposite. For cocoa butter, the position 1 and the position 3, which is, you see, dominant with stearic acids and palmitic acids. Can you see it? If you add them together, the position 1, SN1 and SN3 is almost more than 84 to 88% of this saturated fatty acids. And it's very interesting to see. So number 2 position, 87% is oleic acids, which is a monounsaturated fatty acids. Also, we see lanolenic acids, 8.6%. Okay, because of this position of SN1 to 3 is different. Lard and coconut butter has a very different characteristics regarding melting points. What is cocoa butter made for? Do you know? Did you ever eat chocolate? Cocoa butter. Cocoa butter is a major raw material to make chocolate. Do you ever think chocolate is a magic stuff? Why? In the room temperature, it is solidified. When you put it in the mouth, it's melted. Why? Because the SN2 position is highly opposite by the oleic acids and lanolenic acids. That's the reason why the cocoa butter can use to make a chocolate, and the chocolate shows you a very sharp decrease of the melting points between room temperature and even the mouth temperature. That is a very sharp decrease of melting points between somewhere 25 to 35 degrees Celsius. This is room temperature and this is the mouth temperature. But lard, the pig fat, you're not going to see it. That's why the distribution of these fatty acids in a glycerols is actually related to the melting points. Okay, that's a good example. We will talk about cocoa butter again. It's a very good experimental material to talk about fatty acids. Okay? Okay, wax. This is related to the apple, what we're going to do. Wax is a very long fatty acids, esterized with long chain alcohol, monohydric alcohols. There is 3 major wax, which is carboxylic acid moiety, red alcohol blue. And the example here, supermethylate beeswax and carnival wax. You can see the structure. Ester bonds between fatty acids and the long chain alcohols. It's a protection for leaf and fruits, and for animal feather, which is repairing water, and the protection dehydration. The application in the food products is called coating, cosmetic, lubricants, and polishing inks. Now, the old time, when people just had a hardwood floor, they try to make sure it's clean all the time, and no dust goes there. They put a wax in. Okay, but what's the job? What is the disadvantage of that? People will be easily to fall off because it's too lubricant. So just to let you know, the old time, if you have a Brazilian cherry hardwood floor, people put wax in it, but that's not good. Now apples naturally have some of the waxy. So we want to see the bacteria whether can survive there very well. And we are also trying to work with Casey, trying to using the gas chromatographer to see the different apples, whether they containing different waxy amount. And they do have some of the research project which is done to see the impact of the waxy regarding the bacteria survive on the apple surfaces. Now, organic apple, usually the waxy is natural there, but some of the apples, they use electrolyte spray to spray the waxy on the surface. Okay, so just let you know about that. It's a protection for the animals and the plants. Okay, phospholipids. We want to talk about this. So I left this one here. Phospholipids. Phospholipids. So first of all, you need to know phospholipids is second to glycerols. The amount is second to glycerols in our natural food products. But I tell you the amount is very low, cannot compare to glycerols. So how many we got? 2 to 3% in produce, fruits and vegetables. Seafood, about 0.7% in seafood. Fish, mussels. How about our animal depot meat, like red meat, very low. Maybe around 0.1 to 0.3% in like red meat, very low. Okay, so this is the first thing you need to know. Second, what does this structure looks like? If we still use this figure there, you will see most of them is actually a long chain. So that's even number between 14 to 22. The esterification happened in SN1 and SN2. Phosphate and phosphoric acids add to SN3. So give you an example. This is one of the examples. OCH2, CH2, and plus CH3. This is lecithin. Okay, let's just give an example. Esterification, which also happens right here. This is SN3, which is a fatty, which is a phosphoric acid exclusion. Phosphoric acid exclusion. Okay, so that's something you need to know. Okay, then we want to talk about is what's the function of that. Okay, what is the phospholipids looks like? This is everybody knows. We just review it. There are two. There's the head and the tail. This is hydrophilic, like water. Tail hydrophobic, dislike water, or hate water. There is a two chain. One is saturated, another one is unsaturated. Usually it looks like that. Okay, because it has a head which is hydrophilic, tail is hydrophobic, so it's a very good surfactant. Okay, then what's going to happen? They will be generated a product. So could be looks like this. Looks like a circle. This product, we call it micelle which is using as an emulsification, because as a surfactant to decrease the surface tension between oil, interface of oil and water. Now specifically for one type of the food products, aqueous foods, aqueous foods, this type of the structure, the phospholipids, will create a very special structure called liposome. And this liposome, the function is to prevent oxidation and protect from enzyme activity. Now, what is aqueous foods? Water is a major component, so water foods. Okay? Water is a major component. Now, of course, we know phospholipids can be made as a double layer of a cell membrane in animals, bacteria, and human beings, because they could be connected with protein, become a fluid mosaic model. It's a double layer. Okay? Now, phospholipids actually is very important in the human being and the animals. It's major as a the components of a neurotransmitter. And it is also composed more than 50% of the lipoprotein of HDL. That's one of the reasons the HDL, we call it good cholesterol, could be removed, blood vessel clottings, because of this lipoprotein structure. Okay, so just let you know about that. Phospholipids, which is also very easily to be hydrated because of the hydrophilic heads. So they should be removed. They can be removed from the fats and oil during the refining process. When I wrote that refining process, what means refining process? We want to talk a little bit more. The refining process of the oil refining, or we say, basically is to make raw oil become edible oil. Now what they do, number one, they call it soaping, which is chemical defining. So you're going to have to remove all minor unwanted fatty acids. So oxidized fatty acids. Okay? Number two, we call it a physical. How they do? Degumming. The gums has to go. Number three, we call it deodorization. You're going to have to remove the all the volatiles and also vapor condensers. Okay, so those are the three procedures for the oil refining. And the phospholipids also, we try to remove it. Okay, this is what we have for the phospholipids. Okay, next we want to talk about, briefly, not too complicated, which is one group of the fatty acids, which is actually called unsafenifables. Now, what is unsafenifables? Before we're talking about this, you need to understand what is called saponification. Saponification. Okay, what is saponification? Okay, first the question, how we remove oil and fat? So team, if you do the chicken harvest today, what are you going to do? You use hot water. I know that's one of the methods. What are the methods? Use soap, is that right? Because fat, oil, actually we will say fat or oil reacted with soap in heated alkaline solution with agitation, actually, sometimes. Okay. Now, what is soap? This is soap. Is that right? That is soap. COONA. What is this? Could be any of the fatty acids. If it's palmitic acids, then what's the soap going to be? C15H31COONA. That could be stearic acids. Then C17H35COONA. Okay, this is called saponification. What means unsaponifiable? Those chemical products cannot do this. So back to Tim. When you clean your hands after you processing the chicken the whole day, especially you touch the liver, heart, or those areas, you just throw them away. Did you feel you soap not going to solve all the problem? It's still a little bit sticky sometimes because of the cholesterol, sterols. These are not reacted with soap. So unsaponifiable, very easy to say. Those products are not reacted with soap. Using layman language, very easy to understand. What are they? Sterols, cholesterols, and phytosterols. Now, phytosterols, this is one. Definitely you have to remove during the vegetable oil refining process. Okay, so those are the examples. Now, in our milk fat, 10% of the cholesterol occurs as cholesterol esters. So in our milk fat, they containing about like 10% of the cholesterol. So when you look at the label of the milk fat, you will see. So you can buy a bottle of the milk from the Kroger, you can look at the label. Lots of stories are there. We can, using this class knowledge, we can explain about it. Okay? So we want to explain, introduce you some of the examples of the unsaponificables, briefly. First one is terpene. T-E-R-P-N-E-S, pronounced as terpenes. This is major is found in plants and in animals. Some in animals, major in plants. Okay, what is the characteristic for this one? Remember two, number one. Because of the isoprene units following isoprene law, they must containing anything which is can be integrated number times by 5. So any of them can be divided by 5 equal 2, 3, 4, 5, 6. So the carbon atoms is 5N carbon atoms. Number 2, this is a very volatile compound during the plant metabolism. What I mean the volatile can be evaporated into the air, you will be inhaled. Which is the best one? Which is the most volatile compounds? Is methyl, and the terpenes is the second one. But the level is much lower, so you not even feel about that. You buy a bottle of the methyl, that's not good. You can use mouth, you can use like nose directly to smell it. Your chemistry teacher will tell you have to do like this. You can just put it there. But terpenes, the level is a little bit lower, it's much lower than the methyl. Okay, just want to let you know the example about terpenes. Okay, this is something we want to mention a little bit. Cholesterol. So what is the cholesterol looks like? Cholesterol, we want to talk about the stereo. So you always know this like this. Like that, okay? This is the AB ring, this is CD ring. Now you learn the biochemistry class, maybe chemistry. Label 1, 2, 3, 4, 5, 6. Is there 6 right there? You have to see the label. Sorry, 6 goes here. 6, 7, 8, 9, 10, 11. 11 goes there. 12, 13, 14, 15, 16, and 17. Okay, I remember 19 is from here, 18 somewhere from here. This is the tricky with the chemistry class, sometimes they tested you. So these are the numbers. AB ring, the configuration arrangement is could be cis or trans. But the majority of them, the configuration or the arrangement of CD ring is always trans. This is number one. Number two, our textbook tells you not all the positions have the biological functional components. Most of the time is positions 3, 4, 7, 11, 12, and 17. They are the major position will be attached by something. It could be a hydrogen, or it could be a methyl. Usually the AB could be a hydrogen and a methyl. CD ring is always a methyl, is a dominant. Because attached to there, they will become anything biological function. Now for cholesterol, goes here, we have OH, hydroxy base there. And this is, we also call it a beta configuration. Now, because of this structure, so cholesterol is a precursor of bile acids, vitamin D, another one is like hormones, steroid hormone, like progesterone. Okay? So that's what we have for the cholesterol, and we introduce you something. That's a basic chemistry.